Right beneath one of the most photographed mountains in America, something has been quietly shifting, and almost nobody outside a small circle of scientists noticed until the ground itself started shaking in a way it had never shaken before. This is not a story about an eruption that is coming next week or next month. It is something far more unsettling than that, because what is happening at this volcano right now is not really about fire at all. It is about ice, water, and a slow structural weakening happening in complete silence, thousands of feet beneath a national park, where hundreds of thousands of people hike, camp, and take photographs every single year. And just a few miles downhill from that same mountain, more than 100,000 people are living their daily lives directly on top of the debris field from the last time this thing let go. That is the story we need to talk about today. And once you understand what scientists have actually recorded over the past year, you will understand why officials are calling this the volcano that keeps them up at night. Let's start with where this volcano actually sits on the danger list, because the ranking itself tells you almost everything about why this matters. The United States Geological Survey maintains something called the National Volcanic Threat Assessment, a systematic ranking of every active volcano in the country based on eruptive history, the type of hazards it can produce, and critically, how many people and how much infrastructure sit in the path of those hazards. Most people assume the most dangerous volcano in America must be the one that erupts the most often, and by that measure, Hawaii's Kilauea would win easily. Kilauea has been erupting almost continuously since December 2024, cycling through dozens of individual fountaining episodes, some throwing lava more than 1,000 feet into the air. But danger, in the way scientists define it, is not just about frequency. It is about consequence. And when you weigh consequence, a very different mountain rises to the top of the list, sitting quietly in western Washington state, its glacier-covered summit visible from downtown Seattle on a clear day. That mountain is Mount Rainier, and it has held the designation of America's most dangerous volcano for years, not because it is expected to erupt violently or often, but because of one specific, terrifying characteristic that almost no other volcano in the country shares at this scale. To understand that characteristic, you first need to understand what Rainier actually is physically. At just over 14,400 feet, Rainier is the tallest volcanic peak in the contiguous United States, and it carries the largest single mountain glacial system anywhere in the lower 48, depending on which survey you look at. Somewhere between 26 and 28 named glaciers wrap around its slopes, covering more than 35 square miles of permanent ice and snow. That is an almost unimaginable amount of frozen water sitting directly on top of a mountain that is, geologically speaking, still very much alive. Scientists have calculated that Rainier currently holds roughly 8 times as much glacial ice as Nevado del Ruiz did back in 1985, the Colombian volcano whose eruption melted its ice cap and sent a mudflow through the town of Armero that killed more than 23,000 people in a matter of minutes. That comparison alone should tell you why volcanologists do not sleep easily when they think about Rainier. Now here is the part that makes this mountain uniquely dangerous compared to almost anything else on the Ring of Fire. The primary threat from Mount Rainier is not lava. It is not ashfall, though ashfall is a real concern for aviation and agriculture in the region. The primary threat, the one that keeps emergency planners running drills year after year, is something called a lahar. And understanding exactly what a lahar is and how it forms is the key to understanding everything else in this story. A lahar is a fast-moving slurry of volcanic debris mixed with water, mud, rock, ash, and often entire trees and boulders that flows downhill from a volcano with the speed and destructive power of wet concrete moving at highway speeds. The word itself comes from Indonesian, where volcanic mudflows have caused some of the deadliest disasters in that country's history. Lahars do not require an eruption to happen. That is the single most important and most misunderstood fact about them. All they require is heat, water, and unstable rock. And Rainier has an abundance of all three, sitting on top of each other, right now, whether or not the volcano ever produces another drop of lava. Here is how the mechanism actually works. Deep beneath Rainier's summit, magma has been slowly heating groundwater for thousands of years. That superheated water and steam circulates upward through cracks and fractures in the volcanic rock, and as it does, it chemically alters the minerals in that rock, breaking down strong volcanic stone into something closer to weak, crumbling clay. This process is called hydrothermal alteration, and it has been happening at Rainier continuously for an extraordinarily long time. The result is that large sections of the upper mountain, particularly around the summit and upper flanks, are not solid, stable rock anymore. They are weakened, saturated, structurally compromised material sitting at a steep angle, held in place largely by its own frozen mass and by gravity balancing against friction. Layer 35 square miles of glacial ice directly on top of that weakened rock, and you have built essentially a natural time bomb where the trigger does not need to be volcanic at all. A strong earthquake could do it. An unusually intense rainstorm falling on already saturated slopes could do it. Rapid glacial melt during an especially hot summer could do it. Even a moderate landslide, unrelated to any eruption, could destabilize enough material to send a catastrophic flow of mud and debris crashing down the valleys below. This is precisely what happened roughly 500 years ago in an event geologists call the electron mudflow. There was no eruption, no lava, no explosion. Just a section of hydrothermally weakened rock on the volcano's flank that gave way, mixed with snowmelt and glacial water, and roared down toward what is now the Puget Sound lowlands, burying the area under a wall of debris. It is one of the clearest pieces of physical evidence scientists have that Rainier does not need to erupt to become one of the deadliest natural hazards in North America. And that brings us to why this particular year matters so much, because in the summer of 2025, the ground beneath Rainier did something it had never done in the entire history of modern seismic monitoring at this volcano. On July 8th, in the early hours of the morning, seismic instruments buried around the mountain began registering earthquake after earthquake after earthquake, in a pattern scientists call a swarm. Under normal conditions, Rainier produces somewhere around 9 to 10 small earthquakes a month. That is its baseline heartbeat, the background hum of a mountain with an active hydrothermal system beneath it. Swarms, brief clusters of elevated seismic activity, happen once or twice a year and are considered part of Rainier's normal behavior. But what started on July 8th was not a normal swarm. Within the first 12 hours alone, seismologists at the Pacific Northwest Seismic Network recorded more than 40 events per hour at the peak of activity. By the end of the first week, researchers had located over 1,000 distinct earthquakes. By the time the swarm finally tapered off in late August, total event counts had climbed past 1,300, with some estimates suggesting well over that number once smaller, harder to locate quakes were factored in. To put that in perspective, the previous record holder for the largest swarm ever recorded at Rainier happened back in 2009, when scientists detected roughly 1,000 small earthquakes over the course of 3 days, with a maximum magnitude of 5. The 2025 swarm didn't just match that record. It surpassed it in total number of events, in the rate at which those events occurred, and in the total seismic energy released, stretching not over 3 days, but over nearly 7 weeks. Now, before your mind jumps straight to the word eruption, and I understand why it would, it is critical that we walk through exactly what scientists found when they investigated, because the full picture here is more nuanced and in some ways more interesting than a simple headline would suggest. The United States Geological Survey's Cascades Volcano Observatory, working alongside the Pacific Northwest Seismic Network, immediately activated a broader suite of monitoring tools to figure out what was actually driving this unprecedented seismicity. They looked at ground deformation data from GPS stations positioned around the volcano, checking for the kind of swelling or bulging that typically indicates magma physically pushing upward toward the surface. They found none. No inflation, no deflation. The mountain's shape was not changing. They looked at infrasound sensors, instruments capable of detecting low-frequency sound waves in the atmosphere that can indicate surface disturbances like rock falls or explosions. Nothing unusual showed up there either. They reviewed the network of webcams positioned around the summit and upper slopes, watching for any visible changes to fumaroles, the steam vents that mark where the volcano's hydrothermal system reaches the surface. The webcams showed nothing out of the ordinary. And then, in a move that tells you just how seriously scientists were taking this event, the USGS partnered with the National Park Service to fly a helicopter gas survey directly over Rainier's summit crater on August 4th, specifically to sample the composition and emission rate of volcanic gases escaping from the steam vents in the east and west summit craters. If magma were genuinely rising toward the surface, you would expect to see a measurable shift in gas chemistry, typically an increase in sulfur dioxide relative to other gases. The survey results came back essentially unchanged from previous measurements. No meaningful shift in composition. No meaningful shift in emission rate. So what actually caused more than 1,300 earthquakes to rattle beneath one of the most closely watched volcanoes in the world? The leading scientific explanation is hydrothermal fluid movement. Remember that circulating system of superheated water and steam we talked about earlier, the one slowly weakening the rock around Rainier's summit? Scientists believe that pulses of that fluid, moving through pre-existing fracture networks and fault lines deep in the volcanic edifice, essentially lubricated those fault surfaces, allowing sections of rock to slip against each other and release seismic energy. It is a phenomenon that has been documented at Rainier before, just never at this scale or duration. In official statements released throughout the summer, USGS scientists were direct and consistent in their language, stating explicitly that despite the unprecedented number of earthquakes, the volcano remained at its normal background alert level, colored green on the official warning scale. There was, in their words, no indication that the elevated seismicity represented a precursor to eruption. And by the time scientists conducted their formal review of the data in the weeks that followed, They determined that Rainier's earthquake rate had gradually returned to its typical baseline of roughly 10 events per month, the same rhythm the mountain had kept for decades. Here is where I want you to pause, though, because this is exactly the point in the story where a lot of coverage either overreacts in one direction or underreacts in the other, and neither extreme actually serves you. On one hand, it would be wildly irresponsible to walk away from this thinking Rainier is on the verge of some imminent dramatic eruption. That is simply not what the data shows, and it is not what the scientists monitoring this volcano around the clock are telling us. The alert level never moved. The gas chemistry didn't shift. The ground didn't deform. Every single independent line of evidence pointed toward the same conclusion, that this was a hydrothermal event, not a magmatic one. But, on the other hand, it would be equally irresponsible to treat this as a non-story, because the scientists themselves were careful to note something important in their follow-up reports. They said the hydrothermal processes believed to be driving the swarm may still be continuing at levels too small to generate detectable seismicity, meaning there remains a real possibility of brief flare-ups in activity over the following months. And more importantly, a swarm of this magnitude, the single largest ever instrumentally recorded at this volcano, tells scientists something valuable about how actively Rainier's internal plumbing is moving fluid and heat around beneath the surface, right now, in real time, in a system we still do not fully understand. And this is precisely where the story shifts from being purely about earthquakes to being about the actual hazard that keeps volcanologists awake at night. Because remember what we established earlier. Rainier's greatest danger was never really about whether magma reaches the surface. It is about whether the combination of unstable, hydrothermally weakened rock and 35 square miles of glacial ice above it stays put or gives way. And that second half of the equation, the ice, is changing in ways that have nothing to do with earthquakes at all. Glaciers across Mount Rainier have been retreating for decades as regional temperatures climb, but the pace of that retreat has accelerated sharply in recent years. Researchers monitoring the park have documented multiple named glaciers disappearing entirely, essentially melting away to the point where they no longer meet the scientific definition of an active glacier, a trend playing out across the broader Cascade Range and mirrored in mountain ranges worldwide. Some assessments put the rate of ice loss at several times the historical average. Every summer now regularly produces surges of meltwater far beyond what the mountain's drainage systems were originally built to handle decades ago, sending torrents of water, rock, and debris down established channels in events officials call debris flows, smaller cousins of a true lahar, but destructive in their own right, capable of destroying trails, washing out bridges, and forcing park closures. These debris flows have become frequent enough that Mount Rainier National Park now runs regular staff and visitor education specifically focused on recognizing them and knowing how to get off the valley floor quickly if one occurs. Now let's talk about who is actually standing in the path of the bigger threat. Because this is not an abstract geological curiosity happening in an empty wilderness. This is a hazard sitting directly upstream from real communities, real neighborhoods, and real people, going about their daily lives with almost no visible reminder of what sits above them. Pierce County, Washington, the county containing most of the land downstream from Rainier's most hazardous drainages, has stated that roughly 2.5 million people live across the 6 river valleys that could potentially be affected by a Rainier lahar in some capacity. When you narrow that down specifically to the zones considered to be in direct, high-probability lahar pathways, estimates from geophysicists and volcano hazard specialists put the number at somewhere between 80,000 and 150,000 residents living directly on top of ancient lahar deposits, in towns built, quite literally, on the debris fields of previous catastrophic flows. The towns most frequently named in hazard assessments are Orting, Puyallup, Sumner, and Fife, communities that sit in the Puyallup and Carbon River valleys, precisely the drainage paths that historical lahars have followed on their way down from the summit. Orting in particular has become something of a symbol for this risk, a small growing town built almost entirely within a mapped lahar hazard zone, where local schools conduct evacuation drills, specifically preparing children for the scenario of a lahar warning during school hours. To understand the scale of what these communities are theoretically preparing for, you have to go back roughly 5,600 years to an event geologists call the Osceola mudflow, widely considered the largest lahar to occur at Rainier in the past 10,000 years. At that time, volcanic activity or a related process triggered a massive collapse of already weakened rock on the northeast flank of the mountain, carving out a crater more than a mile wide as the entire mass gave way. As that initial landslide raced downhill, it transformed into a lahar of almost incomprehensible scale, picking up enough volcanic debris, water, and material along the way to fill something in the range of 1.5 million Olympic-sized swimming pools. That flow traveled more than 220 miles from the summit all the way to the shores of Puget Sound, burying what are now the Enumclaw and Kent valleys under a thick layer of volcanic debris, ground that is today home to homes, farms, businesses, and highways. Scientists studying the deposit layers left behind by Rainier's history have identified at least 11 major lahars reaching the Puget lowlands over the past 6,000 years, meaning an event on that scale is not some once-in-planetary history anomaly. It is a recurring feature of how this specific mountain behaves over long timescales. And geologically speaking, we are nowhere close to being overdue for concern to fade. Here's a number that puts real urgency behind the science. When the largest and most fluid lahars race down Rainier's steep upper slopes, they can travel at speeds exceeding 100 miles an hour. Even after they reach the flatter terrain of the Puget lowlands, where the slope decreases and the flow naturally slows, they can still move at 15 to 20 miles an hour, a pace that sounds modest until you remember this is not water. It is a churning wall of mud, boulders, tree trunks, and volcanic debris with the density and destructive force to level buildings, snap bridges, and bury entire neighborhoods in a matter of minutes rather than hours. Geophysicists who have studied this hazard specifically point to towns like Orting, Puyallup, and Sumner as places that could see a lahar arrive with essentially no warning if the trigger were sudden enough, a landslide or a collapse rather than a slowly building eruption sequence that might give scientists days of advance notice. That is the entire reason the region built what is now one of the most sophisticated volcanic hazard monitoring and warning systems in the world, specifically engineered around this one threat. That system, known as the Mount Rainier Lahar Detection and Warning System, was first established back in 1998, developed jointly by the USGS, Washington State's Emergency Management Division, and Pierce County's Department of Emergency Management, in direct response to the recognition of just how vulnerable these communities are. The system works through a network of instruments called acoustic flow monitors, sensors embedded in the ground along the most historically active drainage paths that detect the distinct ground vibrations produced by a lahar moving downstream. When those vibrations are picked up, the data streams instantly to computers at Washington's State Emergency Operations Center and at South Sound 911, both staffed around the clock, where trained personnel can rapidly confirm the signal and trigger the warning half of the system. That warning system includes direct integration with the state's emergency alert system, along with a physical network of outdoor sirens called All Hazard Alert Broadcast Sirens, positioned throughout the most vulnerable valleys, designed to give residents an unmistakable immediate signal that it is time to move to higher ground, right now, without waiting for a phone alert or a news broadcast. And the system has not been sitting static since 1998. Over the past several years, in direct response to growing understanding of exactly how vulnerable this region is, the USGS has been running a major multi-year modernization effort, expanding coverage from the original Carbon and Puyallup drainages to include additional vulnerable paths like the Tahoma Creek and Nisqually River valleys, drainages that were previously outside the system's detection range, despite carrying real hazard potential. New monitoring stations, called lahar monitoring stations, have been installed at sites around the mountain's east and northeast flanks, areas identified specifically because weaker, more collapse-prone rock sites above communities along the White River corridor. These upgraded stations combine seismometers with infrasound sensors, capable of picking up not just the ground shaking caused by an approaching lahar, but also the distinct low-frequency sound waves generated by tons of rock, ice, and debris crashing downhill, giving responders multiple independent confirmation signals rather than relying on a single point of failure. Reporting on this expansion has described it as the most significant overhaul of Rainier's warning infrastructure in the system's entire history, and notably, this modernization effort was already well underway before the historic 2025 earthquake swarm even began, which in hindsight looks like remarkably well-timed foresight from the agencies responsible for keeping these communities safe. There is also something happening in 2026 specifically that deserves attention, because emergency management officials in the region have scheduled what is being described as one of the largest lahar evacuation exercises ever conducted around Mount Rainier, bringing together schools, hospitals, transportation departments, and residents across the most vulnerable valleys to test not just the technology itself, but the human response chain that has to function correctly in the minutes after a warning goes out. These drills matter enormously because, unlike a hurricane, where forecasters can often provide days of advance notice or even most volcanic eruptions, which tend to build gradually through weeks of escalating seismicity that gives officials time to issue warnings, a landslide-triggered lahar at Rainier could theoretically occur with almost no meaningful lead time at all. That means the entire safety margin for tens of thousands of people rests on how quickly a community can move from hearing a siren to actually reaching higher ground. And that kind of margin only exists because of drills, exactly like the ones planned for this year. So where does all of this actually leave us, sitting here in August 2026, looking at a mountain that just produced the largest earthquake swarm in its recorded history, sitting above communities that have spent the past year watching their emergency warning system get its most significant upgrade in decades? The honest answer, the one grounded in what scientists are actually telling us rather than in speculation, is that Mount Rainier remains at its normal alert level today. There is no indication of magma rising toward the surface. There is no indication of an imminent eruption. The elevated seismicity from last summer has settled back into the mountain's typical background rhythm. But normal alert level does not mean zero risk, and it never has for this particular volcano, because the primary hazard here was never contingent on an eruption happening in the first place. It is contingent on the ongoing, decades-long weakening of rock beneath the summit carrying an enormous mass of increasingly unstable glacial ice, a combination that scientists describe not as a question of if a major event eventually happens, but a question of when, on a geological timescale that could mean centuries from now, or could, in theory, mean considerably sooner. What changed over the past year is not the fundamental danger Rainier poses. That danger has been documented and understood for decades. What changed is how loudly the mountain reminded everyone that it is still an active dynamic system, still moving fluid and heat through its internal plumbing, at a scale nobody had witnessed since instrumental monitoring began, right underneath a glacier system that is simultaneously shrinking faster than at almost any point in recorded history. If there is one thing worth genuinely sitting with after everything we have covered, it is the strange asymmetry at the heart of this story. The volcano that draws the most tourists, the one whose silhouette appears on license plates and postcards and coffee mugs across an entire state, is also the one carrying the single most catastrophic lahar potential in the country, not because it is the most explosive or the most chemically volatile, but simply because of geography, because of how much ice sits on top of how much weak rock, directly above how many people. That is not a comfortable fact, and it is not meant to be. It is meant to be a clear-eyed reminder that living near remarkable natural beauty often means living near remarkable natural risk, and that the difference between a close call and a genuine catastrophe frequently comes down to infrastructure most people never think about: sensors buried in remote valleys, sirens tested on quiet afternoons, and drills that ask families to imagine the unimaginable, so that if it ever actually happens, moving fast enough will not require thinking at all. Before we wrap up, here is what actually matters from everything we just covered. First, Mount Rainier is officially recognized as America's most dangerous volcano, not because of eruption frequency, but because of the sheer scale of population and infrastructure sitting in the path of its primary hazard. Second, the primary hazard is a lahar, a volcanic mudflow that does not require an eruption to occur, meaning the danger persists, whether or not the volcano ever becomes explosively active again in our lifetimes. Third, in the summer of 2025, Rainier experienced the largest earthquake swarm ever recorded there, over 1,300 events. And after extensive monitoring across seismic, gas, deformation, and visual data, scientists attributed it to hydrothermal fluid movement rather than rising magma, keeping the volcano at its normal alert level throughout. Fourth, the real long-term concern is the combination of hydrothermally weakened rock and rapidly retreating glacial ice, a mix that has produced major lahars roughly 11 times over the past 6,000 years, and could theoretically be triggered by an earthquake, a landslide, or even an unusually intense period of glacial melt, entirely independent of any volcanic eruption. And fifth, the region's response, an expanding, increasingly sophisticated lahar detection and warning system, paired with large-scale evacuation drills scheduled for this year, represents one of the most serious and well-funded volcanic hazard mitigation efforts anywhere in the world, precisely because officials understand exactly what is at stake for the communities living in Rainier's shadow. If this kind of deep dive into what is actually happening beneath the surface of the natural world is something you want more of, make sure you are subscribed. Because stories like this one, where the real danger is quiet, slow-moving, and easy to miss until the data forces us to pay attention, are exactly what we plan to keep covering. Drop a comment and let us know if you have ever visited Rainier, or if you live in the Pacific Northwest, because the perspective of people actually living near this mountain adds something no report from a distance ever could. And if you found this useful, share it with someone who has family or friends anywhere near Puget Sound, because understanding a risk like this is genuinely one of the most valuable things you can pass along to someone who might need it someday. Stay curious, stay informed, and we will keep watching what the ground beneath our feet is trying to tell us.